Section 4.19. Bands formed from overlapping atomic orbitals. Let's look at this ethylene molecule. On each carbon, there is a p orbital. These two p orbitals can form this pi bonding orbital via constructive interference, or pi star anti-bonding orbital via destructive interference with a node in the middle. And then we can put the two valence electrons in the pi bonding orbital. This is the HOMO, this is the LUMO. Highest occupied, lowest unoccupied. What if we have two double bonds in a conjugated network? This is 1,3-butadiene. And then we have, 1, 2, 3, 4. 4 p orbitals. They can form 4 pi-type molecular orbitals. Over here, 0 node. Over here, 1 node, 2 nodes, 3 nodes. The 4 valence electrons occupy the two lowest MOs. So this is the HOMO. This is the LUMO. We have a gap in between. This is called the HOMO-LUMO gap. So right here, HOMO-LUMO gap. Now what if we have 4 double bonds? And then we have 8 valence electrons occupying the bottom 4, lowest energy MOs. These 4 orbitals are empty. In between, we have a gap, the HOMO-LUMO gap. Now what if we have 2 million electrons? And then they occupy the bottom 1 million MOs. The top 1 million MOs are empty. If we look at this 1 million MOs closely, they have discrete energy levels. But because there are so many energy levels within such a small energy range, it looks like a band. We call this valence band. The valence band is occupied by electrons. Over here we have a million MOs as well. They are unoccupied because the energy spacing between those energy levels is so small. It looks like a band. It's called the conduction band. Now let's look at a different scenario. If we put many atoms together, let's say they are the same type atoms, and it's possible for their individual s orbitals to form a s band. Their p orbitals will form a p band. If there's a large band gap between the s band and p band, it's an insulator. If the band gap is fairly small, very likely you have a semiconductor. If the S band and P band overlap, then you are looking at a metal. So in general, we can draw occupied versus empty bands. But in a metal, you have this kind of situation. Within a band, you have this part unoccupied and this part unoccupied. But this is usually probabilistic. So it's just very likely for these low energy levels to be occupied. Nearly 100% probability. It's very unlikely for those energy levels to be occupied, nearly 0%. So in between, you have a Fermi level. So at this Fermi level, the probability of being occupied is 50%. And this Fermi level is in a metal between the occupied levels and unoccupied levels. Alright? So that's why a metal has a very high conductivity. It's really easy to actually promote an electron from below the Fermi level to above the Fermi level. Now let's look at an insulator we have occupied levels, we have empty energy levels. This is the valence band. This is the conduction band. There's a huge energy gap, and it's impossible to use temperature, to raise the temperature to promote electrons from here to here. An insulator usually has a larger than 4 electron volt band gap. So that's nearly 400 kilojoule per mole energy gap. Again, it's nearly impossible to promote an electron from here to here. And that's why insulators do not conduct electricity. The Fermi level of such an insulator is between the valence band and the conduction band, somewhere in the middle. Again, over here, there's a 50% probability of observing an electron in this level. So now let's look at a new concept. It's so-called density of states. The density of states is simply the number of energy levels divided by this D sub E. So again, between energy E and energy E plus dE, we have a number of molecular orbitals. All right? The number of molecular orbitals or energy levels divided by this dE is the density of states. Usually when we look at a band, usually on the edges you have smaller density, and in the middle you have a higher density of states. So in this case, well, we have a small energy range for this band. We have fairly large density in the middle, fairly small density of states on the edges, the lower edge and the upper edges. Now let's look at 3 different types of solids: metal, semiconductor, and insulator. In insulator, we have a large band gap, usually greater than 4 electron volt. Again, the Fermi level is in the middle. It's really difficult to promote an electron from here to here. That's why an insulator cannot conduct electricity. Semiconductor, they have a smaller band gap between 0.1 and 4 electron volts. The Fermi level is also between the valence band and the conduction band. But because the band gap is so small, sometimes as small as 0.1 electron volt, 1 electron volt is roughly 96 kilojoule per mole. So 0.1 electron volt is roughly 10 kilojoule per mole. So it's possible to just heat up a semiconductor to promote some of the electrons here to here. And then the electrons in this conduction band can move freely. And at the same time, when the electrons leave, some electrons leave the valence band, they will leave some holes here. The holes with a positive charge, they can move around as well. So both the electrons in the empty conduction band, mostly empty conduction band, and the holes in the mostly occupied valence band can conduct electricity. All right, so that's why it's a semiconductor. Other than thermal energy, you can also use a photon to excite an electron from here to here easily. Now let's look at metal. So we have empty bands, we have completely filled valence band, but also in the middle we have partially filled band. And the Fermi level is inside this band. Over here, most energy levels are occupied. Over here, mostly unoccupied energy levels. In between this Fermi energy level is the level at which we have 50% probability of observing this electron. All right, at this Fermi level. A metal can conduct electricity because it's very, very easy to promote an electron from below the Fermi level to above the Fermi level. So over here, these electrons can be easily accelerated. Now let's look at a table of some typical band gaps. Carbon, diamond, has a very large band gap, 5.5 electron volt. This is a good insulator. And down there, silicon, germanium, etc., these four are good semiconductors with a band gap between 0.1 and 4 electron volts. So this one is kind of at the borderline. So this is between a semiconductor and an insulator.